I would like to welcome everyone to our second Cape Center Zoom presentation. And what I would like everyone to do is, as I've previously requested, please do me a favor and just disable your videos for us. Of course, that's going to be everyone except Francois.
Well, I could disable my face as well, and then just have the screen.
Okay, let me just quickly have a quick look at you. Okay, all right. Thank you, everyone. Ian, I see that your video is still on. If you wouldn't mind just disabling it for us, thank you. Great. Okay, welcome everyone. As I said, welcome to the second formal Cape Center Zoom meeting. You know, unfortunately, COVID-19 has forced us to go to move our meeting to online presentations. And you know, the previous meeting that we had was so highly experimental. You know, there were still some bugs that we were sorting out in the background. And we hope that this one is going to go a whole lot smoother. Not that the other one was problematic at all. But I've learned a lot about Zoom in the meantime, so it's going to make the management a whole lot easier. So tonight we've got the privilege of having Dr. Francois Malan join us. And I would like to tell you guys a little bit about Dr. Francois Malan before he shows his very interesting presentation to us. So Dr. Francois Malan holds an MSc in Applied Mathematics from the University of Stellenbosch. And he also holds a PhD in medical imaging from the Leiden University in Netherlands. His background spans several diverse industries, including computational mathematics, orthopedic visualization, the SKA radio telescope project, as well as commercial Earth observation satellite development. So since the beginning of 2020, Francois is employed as an applied geophysicist at the Institute of Mine Seismology, where his work focuses on ambient noise tomography. And that was a whole mouthful. But so what I'm going to do is I'm going to hand over to Francois. Francois is going to be walking us through his presentation and also sharing some video clips with us. Francois, I'm handing over to you.
Thank you, Marius. Yes, so as you saw, I had the privilege of working in quite diverse fields, sort of a bit of a jack of all trade, and the presentation tonight is also a little bit of a jack of all trades because I'm combining a few topics that seem like they might have nothing to do with each other, but they do in fact have a link, and I will try to show this link to you, and hopefully it will be interesting as well. So let's get over to the presentation screen. I need to switch screens at some points during this presentation, so bear with me. If all went well, you should now see the title slide.
Yes, we do. Thank you.
Okay. So tonight I'm going to talk about the South African space industry and our contribution as South African space industry to the NCLE project, that's the Netherlands-China Low Frequency Explorer, and how that ties in with black holes, MeerKAT, and the Square Kilometre Array. Now that seems to almost encompass all of the buzzwords in the South African space industry at the moment. And as I said, maybe you might think, what have these things got to do with each other? So firstly, why do we even talk about this tonight? I think I'm preaching to the choir, but as we all know, space is very inspiring. I mean, even Elon Musk here on the photograph, you can see just the happiness in his face looking at his own creations going up into the sky. It's a very popular thing in the broader public as well. So I got this photograph of the turnout at the launch of the first manned SpaceX mission on the 27th of May. This was during the COVID-19 crisis. I don't know how wise this was, but huge crowds. And really it's our only way to get ourselves off the Earth and to explore the planets around us, which is, I think, one of the big goals for humanity to survive as a species in the long term. But it's also big business. This photograph was taken at the International Astronautical Congress in Bremen, in Germany, where I was lucky to attend this event. And I tried to get a photograph showing just the scale of what goes on here, but actually this conference is spread over so many halls, and this is just a photograph of one of the halls. And what you can see there is just booth after booth of company exhibiting their wares, and it really is a big industry. And when I say space, it mostly, oops, sorry about that. It may, yeah, there we go. It mainly revolves around the satellite industry. So again, all of you would know the first satellite was launched back in 1957, but you know, why are satellites such a big business? What can you do with them? And actually, when you look at it, satellites are only one of 4 things in almost all cases. They either are used for communication, or for taking photographs, or for navigating, or for science. There are a few things that people are talking about that satellites can do in the near future. For example, power generation is one idea, that you have a giant solar cell array in space beaming down the power via laser or something like that to the Earth. Another thing is people are talking about is mining. There are actually companies already doing only that, investigating how we can mine asteroids and stuff like that. And of course, like I said, science. And some of the other exciting science missions of the next few years include the James Webb Space Telescope. That's going to replace the Hubble, essentially. I lost track of when this is going to be launched. I think it was going to be next year. Ketchel would actually know the answer to this. So that's an exciting development. And there are also amazing things, satellites being built to measure gravity waves from space. This is an example of a very exciting mission called LISA, which is going to have 3 satellites orbiting with a distance of 5 million kilometers between them. So this triangle, each leg of the triangle is 5 million kilometers long, and this whole thing is going to orbit behind Earth. On the right hand side is a animation of the Earth, this blue dot, and the red triangle representing the satellites following it. There's an amazing talk that's about, I think, 2 hours long, or an hour and a half, that explains this mission. I can strongly recommend it. If anyone after this has still an appetite for space, just send me a message and I'll send you a link to this. But like I said, I was going to talk about the South African space industry, because all of these things are amazing. And you always think, well, America is doing it, and Russia is doing it, and China is doing it. So firstly, what do I mean by space industry? It's basically manufacturing, launching, operating, and or owning devices that go into orbit of the Earth. And what you might not have known is that South Africa is quite a vibrant sector. In this screenshot, I collected some of the logos of space companies currently operating in the South African and international space market. And actually, almost all of these are near Cape Town. I think the only ones here that are not are the, well, let me quickly see. Pink Matter Solutions is not, and NMMU, but most of these are actually Cape Town, Stellenbosch, and Somerset West. And I think this is something to celebrate, and something not a lot of people realize, not even in South Africa. It's not even known that Africa has that much of a footprint in space. On this map, I colored all the countries in Africa that have national space agencies or space councils. There might even have been 1 or 2 added since I drew this map. So this is already a lot more than many people know. not all of these space agencies own satellites. So if you look at the countries in Africa that own satellites, if you think that about 8,400 satellites have been launched to date, of which 5,000 are still in orbit and only about 2,000 are still working. If you look at all the satellites that were launched, there are about 36 African satellites, and here I show how much has been launched by each country. We are actually, depending on how you count, in second place, sort of just behind Egypt. But the remarkable thing about South Africa is that, again, as far as I know, we are the only country in the whole of Africa who has ever fully developed an indigenous satellite. All of the other countries owning satellites, you know, basically went and asked one of the other spacefaring nations to help them develop it or build it completely. And this has South Africa in this interesting place that if you make a scattered plot and you say, let's put all the spacefaring nations here on this plot, and on the x-axis, horizontal axis, you have the amount of capability, and on the vertical axis, you have the number of space programs and satellites that have already been completed. We are actually sort of going beyond being an emerging space nation into this area of an intermediate space nation in terms of our capability, the horizontal axis, but in terms of the vertical axis of how many satellites and programs we've completed, we are still just starting out. And when I was working in the South African space industry, I think our company and all the others in the area are trying to move South Africa up, like this arrow shows, into this intermediate space nation region to join countries like Brazil and South Korea in terms of space capability. So I'm first going to talk a bit now about how it happened that South Africa actually developed this capability. Why is it that we have knowledge and facilities? So it all starts actually with the previous government in the 1980s, that South Africa decided that we wanted a space program, which was tightly linked to military goals. We actually had nuclear weapons and we were building ballistic missiles, a bit like North Korea maybe is doing at the moment, to put it in a negative way. But back then, there were some very impressive facilities for the time developed. On the left-hand side, you can see the control room of the Overberg test range, which is near Arniston, I believe. And on the right-hand side is one of South Africa's original rockets, called, this one is the RSA-3, and this one is in a museum in Pretoria, I believe. And not only were we working on rockets, but we were also working on satellites. This was all top secret at the time, and I was still in school. Maybe, I don't know, there could even be people in the audience who worked on this. So I hope I don't say anything, anything stupid about it. But South Africa had a satellite that we were developing called GreenSat. And on the left-hand side is a rendition of how GreenSat was supposed to have looked. And to support this whole program, there were very big world-class facilities constructed. For example, HOTEC, which was a secret facility. These days, it's not secret anymore. It's near Grabouw. If you ever drive on the N2 past over Soloris Pass and you drive past Grabouw, at one point there's a sign that says high rising. And if you ever drive up that road for some reason, you'll notice it's a very wide road. It's almost as wide as the N2, and it seems to go nowhere. But when you get to the top of a very big hill, there's a big facility there, and that's HOTEC. It had its own power station and enormous thermal vacuum chambers and electromagnetic test facilities and vibration facilities. And this actually still belongs to the South African government, and we are still maintaining some of this, and some of it is being used for all sorts of engineering processes. So at the end of the sort of apartheid government, the whole government changed, the budgets got reallocated, and this whole program got scrapped. This GreenSat satellite, which would have been an Earth observation satellite, was sort of partially completed, but never to the point where it could be launched, and it stayed on the ground. There's actually, in fact, still a few engineering models standing around at HOTEC and other places. And some of the people who worked on this project were professors at Stellenbosch University, and they thought, well, it's really a shame that South Africa, got so close to building its own satellite, and that all this knowledge could just fade away. So they made an academic program out of it. They got master students involved to build their own satellite at Stellenbosch University. They got the United States to sponsor the launch. And out of this came Sunsat, which was Stellenbosch University satellite. It was launched in 1999, and there's a photograph on the right-hand side of it attached to the launch vehicle, around this whole central pillar. There's the nose cone encloses the whole thing. And this satellite was also Earth observation satellite. It took images from space, and it worked quite well for quite a few years. It was considered a big success. And the next important milestone, I think, in South Africa's space heritage is Mark Shuttleworth, who really inspired the nation when in 2002, he became the first African astronaut or cosmonaut on board the International Space Station. And of course, after that, he went on to found Ubuntu Linux, the operating system that's still also being used around the world. So he really did a lot for showing the world what South Africa can do. And then after that, there was another satellite, again developed in Stellenbosch, this time by a company called Sunspace, which was a commercial spin-off of the Stellenbosch University. And this was bought by the South African government. And 10 years after Sunspace, we had Sumandila Sat launched into space. Again, an Earth observation satellite taking pictures of the surface of the Earth, this time in more spectral bands and at higher resolution than the original Sunsat did. And South Africa seems to have this cadence of developing its own government satellite about every 10 years. So after Simbandila Sat, there was a new project called EOSat-1, which was started in 2012. And if they kept to this 10-year schedule, it should have been launched in 2019. And I think that was originally the plan. But as you all know, the government's finances is a bit uncertain, and this project has been on ice a few times. And at the moment, I think the future of this is still uncertain. So, of course, this is, as you might have guessed, again, an Earth observation satellite. That seems to be what South Africa has developed as its speciality. The EO in EOSat stands for Earth observation. At the same time, there were other institutions that also got into the space race. For example, CPUT, the Cape Peninsula University of Technology, developed a tiny little satellite called ChipisoSat in 2013. Keeping with the theme, this satellite also had a camera on board, a very small camera. This whole satellite is only 10 by 10 by 10 centimeters. This is what's called a CubeSat. CubeSats started out as toys, and over the years, people managed to fit more and more capability into them. And these days, CubeSats can actually perform useful functions. So you can see in this photograph on the right, that little circle is literally a key ring. That's how small the whole satellite is. This satellite was a success as well. And South Africa's next two satellites developed at home were these two. Also CubeSats. These are 10 by 10 by 20 centimeters large. So they are literally like two of these cubes stacked on top of each other. And these two that shared a lot of their design were called ZA Aerosat on the left, developed by Stellenbosch University, and InSight-1, which is South Africa's first commercially developed satellite. And this satellite was developed by SCS, the company I worked for at the time. And I will come back to talk about this satellite, because this led to a whole chain of events that I will explain shortly. After these two satellites, both of which have since been launched, re-entered the Earth's atmosphere, there was another satellite developed by CPUT called ZA-Cube-2. This time it's a 3U satellite, so it's actually like 3 of those cubes stacked on top of each other. And the purpose of this satellite is, among others, for fire detection. So it has 2 cameras that can detect fires burning in infrared, essentially on the surface of Earth. And yeah, during the terrible wildfires in Australia, for example, and also in South Africa, these satellites can give firefighters real-time information about where to go to and what's going on. But let me quickly return to InSight 1. So this is a younger me on the right-hand side and one of my fellow engineers on the left-hand side. And there you can see how small the satellite is in real. This is the actual satellite behind us. We're not contaminating it by being so close. The satellite behind us is actually in an extraction case that filters the air. This was after it was completed and just before it was delivered to the launch facility. Now, if you take that satellite and pull away its panels, here's a illustration of some of the things that went on inside. And all the components shown in red were completely developed in South Africa. So I think this is really something to be proud of, all the capability that exists. Some of these were done by commercial companies, some were done by universities. And the main payload on the satellite, the main functional thing, was a little camera called the Gecko. And here it is. That's my own hand inside the glove on this photograph. And this camera was completely developed by South African engineers and included in the satellite. It was deployed from the International Space Station on the 25th of May, 2017. How it worked is that these small satellites, they actually took it along with the cargo to the space station, like together with all the food and other stuff. They take that to the astronauts. They packed these satellites in a box. Once there, they took the box through the airlock to the outside, and the box is basically spring-loaded. So at some point, the flap opens and the spring pushes out the satellites. In this photograph, there are actually 3 little satellites behind each other. The tube in which they go is 60 centimeters deep. And InSight 1, the satellite we built, is the one in front of these 3. So the close-up shows this is InSight 1, and behind it are 2 other satellites. And eventually they drift apart into the same orbit. As I said, this camera's main goal was to take photographs. And the very first photograph we got from space from the satellite was this one, taken over British Columbia on the 25th of June. So that will, tomorrow, it will be the 3-year anniversary of this photograph we got from space. It was amazing. If any of you saw the movie Lion, about the Indian boy who gets separated from his family and he doesn't know where he grew up. And then as an adult, he sits with Google Earth and he tries to find the town, he tries to follow the train track by which he traveled, and until he sees something familiar, and then he recognizes some tower, and then he's suddenly, filled with emotion. In this case, we got the photograph, but we didn't know exactly where the satellite was when it took the photograph. So I literally sat with Google Earth and scrolled around, and I knew it was somewhere in Canada, and you could see this road here, and it has sort of this kink, and I was looking for roads that had a kink like that. It was a very special moment. So after this successful first photograph, this satellite went on to take some other really beautiful ones. I'm just showing some here for your interest. This one taken over the town of Parijs in the Free State. This is the Vredefort Dome. You can see sort of the half circular shape, which is remnants of an ancient impact crater, very ancient, that one can still see from space. We even managed to detect some ships with this. This photo was taken over the Wild Coast in the Eastern Cape. And if you zoom in there, you can see a tiny little ship traveling towards the east. And interestingly, this ship was not transmitting its position via the AIS system, as all ships are actually required to do. So you could use a satellite like this to find illegal fishing vessels in principle. I don't think this was one of them, but this is definitely a use case for protecting our waters. From 2018, another very beautiful photograph taken over Bear Lake in northern Utah. This specific lake has sediments washing into it, causing this very bright blue color to show up where the sediments swirl into the water. And you can also see some of these circular spillplanter, these circular irrigated areas. These are not alien circles, but irrigation circles. The very last image from the satellite was on the 23rd of April this year. And about a few days after this photograph was taken over the Babiaans Kloof, the satellite fell down into the Earth's atmosphere and burned out as a little shooting star. But this satellite led to a lot of things. And in case you're wondering how I'm going with this talk to, if I'll ever end up at black holes, I'll get there. And I'll show you how. So this little camera that we developed called the Gecko was developed further, went through a few iterations. It became a commercial product that was sold to several other space programs where they wanted a little camera taking high quality photographs. The one on the right hand side is an even larger camera that was developed using similar technology. Here you could even go online and buy the Gecko camera. This is on a site called CubeSat Shop, only 23,000 euros and it's yours. But it also led to us developing much larger and more capable cameras. So here's a photograph of my colleague Brian Dean, who's now CEO of his own space company based in Stellenbosch in Technopark. Back when he was a project engineer working on the sort of engineering model for this larger imager. And this specific imager that was called the Tegu, this one could take photographs with a 2-meter resolution, much better than the 40 meters of this tiny little Gecko camera. And this was included on a Pakistani satellite, Paktes 1A, that was launched in 2018, also very successful. And this technology that we were developed, we got the chance together with all the other South African space agencies to, we travel to the world, we go to these space conferences and we show the world what South Africa is capable of. And you stand there as the only African booth most often, and it's a really proud moment to be able to do that. But developing this technology unexpectedly got us involved in this project called NCLE. So now I'm going to make the first big pivot of this talk, and I'm going to move to radio astronomy from space and the Chinese space program. And how these are linked is that, well, the NCLE project is a high-level agreement between the governments of the Netherlands and China. On the top right, you can see the photographs from the signing ceremony with the King of the Netherlands, Willem-Alexander, next to the President of China and his wife, and both of their wives. And South Africa is not part of this collaboration officially, but in this mission, the Dutch developed a science instrument. And part of the science instrument is that they basically needed a processor and a flash drive, essentially, something that can compute results from data and store lots of data onto flash memory. And they needed it quickly. And this part here is the data processing box of this Tegu imager I just showed. And this technology grew out of the little Gecko camera I had in my hand in the other photograph, which traces its way all the way back to South Africa's earlier space programs. But inside this box, basically, we had exactly what they needed: processors and memory chips that were designed to work in space. And this mission is part of China's space program called the Chang'e 4 mission. Chang'e is a series of missions. There are 6 of them in total. The dates here are as it was when I gave the talk the first time. I think it might have been all pushed out a bit because this number 5 hasn't yet flown and it's already 2020. But allow me to first explain a bit about the Chang'e mission, because this will now set the scene for the black holes that come later and the radio astronomy that I'm going to talk about. So this might be a good, I'll show you a little mission shortly, a little video shortly about the mission. But basically Chang'e 3, the third one, was a little lunar lander that this is a, I think, slightly photoshopped photograph from the government of China. They are known to Photoshop things sometimes, but essentially it's a real photograph. You could just ask yourself who took the photo in this case. Chang'e 3 consisted of a lander and a little rover, and the rover drove away from the lander, and each of them had a camera. So I think they took the photo that the lander took of the rover and the photo that the rover took of the lander and composited them together into this photograph here. And being a success, Chang'e 4, which was originally a backup mission for if something went wrong with Chang'e 3, was expanded to include more science. And 2 things that they did is they said, okay, they want a different landing site and more science to be done on this mission. So the Chang'e 3 mission landed on the moon, and this is essentially the moon as seen from Earth, more or less. So the landing site was on the Earth-facing side of the moon. For Chang'e 4, they decided, well, let's land on the far side of the moon. You might be familiar with the dark side of the moon, the Pink Floyd album. People always talk about the dark side of the moon, but actually there's no side of the moon that's always dark. Each point on the lunar sort of equator gets a day and night. But there is indeed a far side of the moon. I don't know if you know the cartoon called Far Side by Gary Larson. But what happens is, and again, I think I'm preaching to the choir here, so forgive me if I bore you with this, but the moon turns in such a way around the Earth that it's tidally locked, and the same side of the moon is always facing Earth. So the problem is when you land your little spaceship on the far side of the moon, you basically have no direct line of sight to the surface of the Earth ever. And to overcome this problem, they decided for Chang'e 4, they are going to add a third component, and that is this relay satellite that is basically going to bounce the signal from the lander via the satellite to Earth. And to make this work, they placed this relay satellite around a point called the second Lagrange point, the L2 point, which is a special point where the gravity of the Earth and the moon cancel out in such a way that if you place something at L2, it rotates around the Earth at the same rate as the moon does. So there you can see the concept. There are also 4 other points that do the same thing, one between the Earth and the moon, one on the other side of the Earth relative to the moon. And interestingly, you have with the sun and the Earth similar points. There's also a L2, 1, 2, 3, 4, 5 sun-Earth point. And here's an illustration of how L2 goes around Earth. And the relay satellite is not exactly at L2, because if it was exactly at L2, the Earth would block, the moon would block the view from Earth, and you won't be able to communicate with the relay satellite. So what happens is they actually orbit this satellite around L2 so that we can always sort of look past the moon at it. And being at this location, so far away from Earth on the far side of the moon, they figured this is actually a great place to add some science instruments as well. I'll get to that in a bit. But I first want to now that I explained the basics, I want to show you a little video explaining the mission. It's with Chinese subtitles, so allow me to switch screens quickly. This should work now. You'll see the video pop up in a second. So let's see. I practiced this, so I should be able to figure out how to do this again. Wait a moment. Sorry, Marius, I'm thinking now, I'm trying to find that share audio button that I just had. Hang on. I got the video open, and now I need to okay, so that should be the video, and please excuse the delay. We're good to go. So this video was created as a sort of a promo by the Chinese Space Agency to showcase all of these Chinese missions. You can see the L2 point that I just talked about. There's the lunar lander touching down, Chang'e 3. This first little rover that they built didn't last very long, actually. The second one on Chang'e 4 actually survived for a long time. The challenge with the moon is that the days are very long. It's half a month long, and the nights are half a month long. So the poor little lander gets baked in the sun, and then it gets extremely cold during the long night. There's Chang'e, that's the actual launch of our little bit of South African space heritage on board. There's the relay satellite unfolding its antennas, traveling to the L2 point. There's it's doing its relay function. and again the little lander and the little rover. And these are the future missions that, as far as I know, haven't yet taken place, to actually collect samples from the moon and return it to Earth. I'll cut the video short here. So that was the Changi series of missions. So now let's go back to the presentation. See if I can do this a little bit quicker than the previous. Doesn't seem like it. Bear with me. We were right here. Okay. I'll get the hang of this in on later. Okay, we're back. So as you saw, this is the spacecraft that was launched, the Changi 4 spacecraft. When it unfolds, it looks something like this. And inside of the spacecraft is this little black box in which our hardware went, and actually worked very well. As far as we can tell, they were successful. They got some very good astronomical data. And the question is, why go to all this trouble? What were they doing? And what they did is they actually, except for being a first in many ways, it was also the first radio telescope looking at low frequency radio waves. And there's a reason it's never been done before. Over here is some photographs of how the development worked, developing this board. We had to bake it in ovens and shake it and make sure it worked. And there's the little board as it was developed to the Dutch, who then put it in their instrument. That looked like that. That went into the satellite. Over here you can see again the photograph of the launch. And in space, there's this photograph that I find really amazing once you know what you're looking at. This is taken from the L2 point, and with some headings. There in the foreground you can see the moon, and in the far background is the Earth. The L2 point is actually that far beyond the moon that the Earth looks tiny and far in the distance. This camera that took this was sort of recessed in the satellite, so you also see parts of the satellite in the foreground, blocking the view a bit. And the reason one wanted this radio telescope there is that if you're on the surface of Earth, you can see through the atmosphere with visible light, and you can look through the atmosphere in the radio waves range. But what this brown line here at the bottom shows is that all other frequencies, shorter wavelength than optical, for example, ultraviolet and X-rays and gamma rays, get blocked by the Earth's atmosphere, which is amazing because those rays are quite damaging to us humans. But also longer wavelengths beyond infrared get blocked, and then the very long radio waves that sort of beyond VHF also get blocked by the Earth's ionosphere. And the radio telescope that the Dutch built, to which we contributed, that was on the satellite, specifically looks at these very long wavelengths. And to look at them, you need to have an instrument in space. And the reason they wanted to look at these long wavelengths is that looking, because you have this redshift, that light traveling from objects that are moving away from us sort of gets stretched longer and longer, the same way an ambulance signal goes like beep, or beep, or beep, like that. You get the same with light that becomes radio waves, that become very long radio waves. And eventually, if you want to look back to the very first parts of the development of the universe, shortly after the Big Bang, you basically have to look at these very long wavelengths that you cannot detect from the surface of the Earth. And it's at this point where I'm not going to talk more about the Big Bang, but actually going to talk about radio telescopes and what you can see with them. So this is the next big pivot in the talk. So this is the last phase. And you can ask yourself, what is it that you can actually see from a space-based platform? Here are 4 possibilities. You can look at electromagnetic waves because they travel through vacuum. You can look at high energy particles because they basically get this, like the solar wind, for example, they get emitted and they just travel through space. You can look at gravity waves. As I said, there was that amazing talk. I can point anyone who's interested into that talk about that. That's quite a recent discovery. I mean, Einstein formulated that there will be things like gravity waves, but he thought one wouldn't necessarily ever be able to detect something that would be sensitive enough to measure them. And lastly, you can put instruments on board your satellite and look inside the little satellite. But gravity wave detectors are massive. High energy particles are, you're limited. You can't look at stars far away. You can basically only detect them from the sun itself. So almost all things that one looks at on a satellite are electromagnetic waves. And the nice thing about it is you can look at the same thing in different wavelengths and you see different structures. So for example, here is the Crab Nebula. If you look at it in radio waves or infrared or visible light or ultraviolet or X-rays, for each of these, you need different instruments. And like I said, the Earth's atmosphere blocks some of these waves. So for example, to look at this low energy X-rays, one needs also an X-ray sensitive telescope in space. Again, going back to that, these 2 green regions are the only 2 windows through which we can look at space from the surface of the Earth. Essentially, the visible light sort of window and then radio waves. So many of you have your own telescopes looking at visible light, but in South Africa, we also have this great thing, the MeerKAT and the square kilometer array looking at radio waves. And here is a photograph of how MeerKAT sees the Milky Way, for example. This photograph was quite a big event when it was released to the public a few years ago. And a big improvement on all previous radio telescope photographs. But then there's this other photo that you might have seen in the news last year, this one. And what is this then? So you might know that this was the first ever photograph taken of a black hole, and the press went wild and made lots of joke about it too. But this was really an enormous achievement. And the question is, how is it possible that we could take a photograph of a black hole? Because even though black holes are quite big, they are all very far away. And that's good because they would have destroyed the Earth if they were closer. But a telescope wouldn't normally ever have even nearly the resolution to make out any structure of a star-like object at the distances that stars are, except for our own sun. And what made this possible is something called radio interferometry, which I can't explain in a short talk like this, and you really need an expert in that to explain it, which I'm not. But what you do with radio interferometry is instead of having one big telescope, you have multiple telescopes that are far away, and you combine the signal you get from these different telescopes in a very clever way. And that allows you to get much more resolution, similar resolution, in fact, as you would have gotten from a telescope that was the size of the distance between your different individual telescopes. And this has been something that's been done for some time. Some of the famous radio interferometers is this one, the VLA in the USA, that's featured in the movie Contact. And there's one in Chile that's called ALMA. And then we have our very own MeerKAT array near Carnarvon in the Northern Cape. Here's a photograph of these dishes. It consists of 64 dishes, and this is the precursor to the square kilometer array, which Ketchel, who's in this call, also worked on, and I also worked on it briefly. And this, the full size array will consist of more than 250 of these 15-meter dishes. But not only is the number of dishes important and how big they are, but it's also very important how you place these dishes. So here is an example of one of the proposed layouts for how these dishes would be placed. You have in the middle of this star-like structure a very dense area that gives you sensitivity to be able to see faint objects. But then you have dishes that are very far away, and that long distance, as I explained, allows you to see very small details. In the Netherlands, they have a radio telescope called LOFAR, and here you can see where all the components of this extended LOFAR array will be placed or have been placed, and this just gives you an idea of the scale of this telescope. You have a telescope that spans basically the size of Europe to be able to see very fine details. And people have taken this even further and decided, well, you can have telescopes on different parts of the Earth's surface, on different continents. And if you can combine those signals in the right way, you can see very, very small things. And that is, in fact, exactly what they did to be able to see the black hole. And so what they took telescopes all across the surface of the world, and they combined them together, the signals, and they were able to tease out this photograph of the black hole that you see here on the left. But if they had telescopes that were even further apart from each other, one might have been able to see even more details. And then they expect, according to simulations, that what you see on the left is actually a bit of a blurry image of what you see on the right. But the question is, how could you ever get telescopes further apart than on different continents? And the solution is put one on the moon, for example, or at the L2 point beyond the moon. So this humble little instrument that we helped develop is a pathfinder for building what would eventually possibly be a radio telescope that has parts orbiting beyond the moon, that could be on the moon and on the Earth, and we can combine all of these to see black holes and other objects in detail that one cannot see in any way with any single telescope, no matter how large you build it. So that's how all of these things fit together, and it was an enormous privilege being part of this. And I see I still have a few minutes left, and I want to finish by showing you a video that ties onto this talk, that explains what it is that you see in this image on the left-hand side, because this really blew my mind. First, I'm gonna show two little videos. The first one is from the movie Interstellar, which I don't know if you saw that movie, but I will play the relevant part from it. So here we go again. Let's see if I can do it quicker this time. I need to go to 1 hour and 5 minutes and 20 seconds. Okay, and there we go. So if all went well, you will now see a still from the movie.
Are you reading these forces?
Unbelievable.
The literal heart of darkness.
And there it is, this still frame. And when I saw this the first time, I thought, wow, this looks really cool. Maybe they just got some artist to draw something that looks amazing. I mean, this isn't based on anything physical. You wouldn't be able to see a black hole, right? A black hole is black. Why? So, but it looks cool. And it turns out that this animation here was actually based on real good science. They got some real experts in. They did the simulations, and this was the first time that anyone ever visualized how a black hole would look. And this was before this photograph was taken. And it turns out, I think they were right. And what goes on in this video I'm going to show you now. This video is actually on YouTube as well, but I really was blown away by it. So it's about a few minutes long. So let's share that screen. Here we go.
On Wednesday, April 10th, 2019, you will probably see the first ever image of a black hole. That's when the Event Horizon Telescope will be releasing their results. And I haven't seen them yet, but I think they're going to look something like this. And I can be relatively confident because, well, it's going to look a bit like a fuzzy coffee mug stain. But if you are disappointed by this image, I think that misses the gravity of the situation. From this image, we should be able to tell whether the general theory of relativity accurately predicts what happens in the strong gravity regime, that is, what happens around a black hole. What I want to do here is understand what exactly we are seeing in this image. So here is my mock black hole of science. And this sphere represents the event horizon. That is the location from which not even light fired radially away from the black hole could be detected by an outside observer. All of the world lines end up in the center of the black hole in the singularity. Once you're inside here, there's no coming back, not even for light. The radius of the event horizon is known as the Schwarzschild radius. Now, if we were just to look at a black hole with nothing around it, we would not be able to make an image like this because, well, it would just absorb all electromagnetic radiation that falls on it. But the black hole that they're looking at, specifically the one in the center of our Milky Way galaxy, Sagittarius A star, has matter around it in an accretion disk. In this accretion disk, there is dust and gas swirling around here very chaotically. It's incredibly hot. We're talking millions of degrees, and it's going really fast, a significant fraction of the speed of light. And it's this matter that the black hole feeds off and gets bigger and bigger over time. But you'll notice that the accretion disk does not extend all the way into the event horizon. Why is that? Well, that's because there is an innermost stable circular orbit. And for matter around a non-spinning black hole, that orbit is at 3 Schwarzschild radii. Now, in all likelihood, the black hole at the center of our galaxy will be spinning, but for simplicity, I'm just considering the non-spinning case. You can see my video on spinning black holes if you want to find out more about that. So this is the innermost orbit for matter going around the black hole. If it goes inside this orbit, it very quickly goes into the center of the black hole and we never hear from it again. But there is something that can orbit closer to the black hole, and that is light. Because light has no mass, it can actually orbit at 1.5 Schwarzschild radii. Now here I'm representing it with a ring, but really this could be in any orientation. So it's a sphere of photon orbits. And if you were standing there, of course you could never go there, but if you could look forward and actually see the back of your head, because the photons could go around and complete that orbit. Now, the photon sphere is an unstable orbit, meaning eventually either the photons have to spiral into the singularity or spiral out and head off to infinity. Now, the question I want to answer is, what does this black quote-unquote shadow in the image correspond to in this picture of what's actually going on around the black hole? Is it the event horizon? Are we simply looking at this? Or is it the photon sphere or the innermost stable circular orbit? Well, things are complicated. And the reason is this black hole warps space-time around it, which changes the path of light rays. So they don't just go in straight lines like we normally imagine that they do. I mean, they are going in straight lines, but space-time's curved, so yeah, they go in curves. So the best way to think of this is maybe to imagine parallel light rays coming in from the observer and striking this geometry here. Of course, if the parallel light rays cross the event horizon, we'll never see them again, so they're gone. That will definitely be a dark region. But if a light ray comes in just above the event horizon, it too will get bent and end up crossing the event horizon. It ends up in the black hole. Even a light ray coming in the same distance away as the photon sphere will end up getting warped into the black hole and curving across the event horizon. So in order for you to get a parallel ray which does not end up in the black hole, you actually have to go out 2.6 radii away. If a light ray comes in 2.6 Schwarzschild radii away, it will just graze the photon sphere at its closest approach, and then it will go off to infinity. And so the resulting shadow that we get looks like this. It is 2.6 times bigger than the event horizon. And you say, what are we really looking at here? What is this shadow? Well, in the center of it is the event horizon. It maps pretty cleanly onto the center of this shadow. But if you think about it, light rays going above or below also end up crossing the event horizon just on the back side. So in fact, what we get is the whole back side of the event horizon mapped onto a ring on this shadow. So looking from our one point in space at the black hole, we actually get to see the entirety of the black hole's event horizon. I mean, maybe it's silly to talk about seeing it because it's completely black. But that really is where the points would map to on this shadow. It gets weirder than that. Because the light can come in and go around the back and, say, get absorbed in the front, you get another image of the entire horizon next to that, and another annular ring, and then another one after that, and another one after that. And you get basically infinite images of the event horizon as you approach the edge of this shadow. So what is the first light that we can see? It is those light rays that come in at just such an angle that they graze the photon sphere and then end up at our telescopes. And they produce a shadow which is 2.6 times the size of the event horizon. So this is roughly what we'd see if we happen to be looking perpendicular to the accretion disk. But more likely, we will be looking at some sort of random angle to the accretion disk. We may be even looking edge on. And in that case, do we see this shadow of the black hole? You might think that we wouldn't. But the truth is, because of the way the black hole warps space-time and bends light rays, we actually see the back of the accretion disk. The way it works is light rays coming off the accretion disk bend over the top and end up coming to our telescopes. So what we end up seeing is something that looks like that. Similarly, light from the bottom of the accretion disk comes underneath, gets bent underneath the black hole, and comes towards us like that. And this is where we get an image that looks something like the interstellar black hole. It gets even crazier than this, because light that comes off the top of the accretion disk here can go around the back of the black hole, graze the photon sphere, and come out the bottom right here, producing a very thin ring underneath the shadow. Similarly, light from underneath the accretion disk in the front can go underneath and around the back and come out over the top, which is why we see this ring of light here. This is what we could see if we were very close to the black hole, something that looks truly spectacular. One other really important effect to consider is that the matter in this accretion disk is going very fast. close to the speed of light. And so if it's coming towards us, it's going to look much brighter than if it's going away. That's called relativistic beaming or Doppler beaming. And so one side of the accretion disk is going to look much brighter than the other, and that's why we're going to see a bright spot in our image. So hopefully this gives you an idea of what we're really looking at when we look at an image of a black hole. If you have any questions about any of this, please.
And yeah, I'm going to stop it there. So that was a bit of a cheat, getting someone else to finish the presentation, but I just thought this guy explained it so well and so beautifully, and it's absolutely magnificent. Thank you very much. I know this was long, but I'm done with my part now, so if there are any questions, I'd be happy to try and answer them.
Oh, thank you, Francois. That was really fantastic. We really enjoyed it, and thank you for sharing those video clips with us. You know, I think our practicing really paid off. Yes, so as you said, we're going to allow people to ask questions. So you can either use the raise hand function in Zoom, or you can even ask your question via the chat window as well. So yeah, please feel free to ask Francois a couple of questions.
Not everyone at once, please.
Yeah, I think what we can also do is hello, Chris.
Yes, I just want
How
to know
long are these satellites powered for?
Sorry, Chris, we got Chris de Koning and other Chris asking, so I'm going to queue them. So I'm going to ask Chris de Koning to first ask his question, and then I'll ask Chris Forder to follow him.
Okay, excellent talk. I loved it. I just want to know, when they launched the CubeSats from those, I think you said from the space station, with the spring-loaded, how accurate could they get something into orbit, the exact speed, the exact direction? Isn't that a bit hit and miss, or can they do it very accurately?
I think one has to keep in mind that the space station is moving relative to us at around 7 kilometers per second. And the relative speed by which you push the satellite away is very, very slow. It's sort of a gentle, I don't know exactly how fast it is, but maybe 1 kilometer per second or something. So it's a very gentle push. So seen from our perspective on Earth, the satellites are all in exactly the same orbit, essentially. There's no real right or wrong. You can go a little bit faster at the one side or the other side. Over time, they drift away from, let's say you push it away at 1 kilometer per second, it keeps on drifting away at 1 kilometer per second. And after a few hours, it's very far away. And because they have different drag and different shapes, even at 400 kilometers altitude, the atmosphere drags them down a little bit, and that's why they eventually fall back. So over time, the orbits diverge further and further, and they never see each other again, essentially. The exact orbit doesn't really matter so much at that scale of small differences. You basically say it's at this inclination at 400 kilometers altitude and more or less circular, and the satellite can determine its own position. So it has a star camera that can look at its position relative to the stars, and it can detect where the sun is, and some of them can even detect GPS signals from the GPS satellites. So as long as the satellite knows where it is, it doesn't really matter exactly where it is, as long as it's not on a collision course with another satellite, of course.
Well, thank you so much for answering that first. So, Chris Forder.
Thanks for the talk, Francois. The little satellites that you showed had small power packs in them. How long do they last, and are they recharged then with solar panels?
Yes, essentially, basically all satellites orbiting Earth have solar panels these days. The original Sputnik did not. It was just this steel ball, essentially with 4 antennas, and I assume it had some battery inside that lasted for a certain amount of time. Sputnik also didn't do that much, it just broadcast a little radio signal. But all satellites orbiting Earth have solar panels, and for times when it needs more power or when it passes through the shadow of the Earth, it has lithium-ion batteries like you have in your cell phone, for example, that get charged from the solar panels. But all power in space, for almost all space operations, is derived from the sun. And the sun really gives a lot of power. You have more than 1 kilowatt per square meter that you can try and harvest. It's only for missions that, for example, go very far away from Earth. Like there was this Rosetta mission that that was actually also solar panel powered, but that mission was the European mission where they landed on a comet. And for that mission, they had needed massive solar panels that sort of concertinaed out, because when you're far away, the solar power is very weak. And the Voyager missions and the Pioneer missions that are now traveling out into deep space, they have a nuclear power source on board that provides power. But for everything that's sort of close to the sun at Earth distance, you can use solar panels.
Excellent. Thank you, Francois. So I think we've got Rudolph that's got his hand up. Rudolph?
Hi. Firstly, thank you very much for the talk. And I'm not sure if it was intentional, but the choice of video you have there from Veritasium is very apt. His parents are both South Africans who moved to Australia, and that's where they had him. So he's nearly South African.
Oh, thanks.
So,
I didn't know that.
his name is Derek Miller. Very cool guy. I love his channel. But the question part, does it make you feel proud, or does it give you a sense of accomplishment knowing that there's something zooming around our globe looking down back at us?
Something that we helped build, or just generally?
Specifically you.
Well, yeah, I mean, I don't think about it all the time, of course, but you know, it definitely gives a warm, fuzzy feeling, because, you know, people who work in the space industry, it sounds very glamorous, but one can probably earn a lot more money by being a chartered accountant or something else. So, and the actual work one does isn't always that glamorous, but when something like this works, it's really quite special. It's unfortunately, South Africa has had all these companies start up, but also many of them sort of failed along the way. Sunspace that I mentioned no longer exists. Space Advisory Company, where I worked for, is also now kind of no longer in its original shape. It's tough to make a good business case out of something that inspires you and that you love. So, but there's always some people who then take the baton and go on and say, like, oh, others have failed, but we will make it work.
Awesome. Thank you very much.
Thank you, Rudolph. Anyone else got any more questions? If you know, you guys can also just unmute yourselves and ask the question.
Maurice, I've got a question.
Hi, Richard.
Hi. Thanks. A very nice talk. Thanks a lot. With regard to the interferometer of the radio telescopes, for example, the MeerKAT, you said the central portion is dense for the sensitivity, and the further out portions are for the resolution. But if you're looking at a very faint object that the central portion can only just detect, surely the outside portions have to have equivalent sensitivity, otherwise you won't get any signal from them.
I think you are right. So you probably won't be able to use the interferometry part as an interferometer necessarily if you are looking at signals that are so faint that you can barely detect them with a single dish. Yeah, you'll actually have to ask a radio astronomer that question. I'm not well enough versed to tell you that with 100% certainty. But some of the things that for example, this black hole, I believe, emits that was detected, emits actually quite a lot of energy. but in this case, the challenge was to actually see any structure in it and not just see a white pixel.
Okay, thanks.
Thank you, Richard. Anyone else?
Yeah, I wanted to just add to that. The SKA project and MeerKAT, they have a long list of science goals, science objectives that they want to do with it. So it's not just built for one thing. For example, they say, okay, with this new telescope, we are going to make a map of all the pulsars that were previously undiscovered, and we are going to try and look back to the very early stages of just after the Big Bang. And on top of that, we maybe can look for let's say Earth-like planets or something. And we can maybe detect aliens if there are aliens. And we can, so it's this long list of things. And for that reason, the instrument also has different modes in which it can operate. So in some modes, you might set it up to be specifically sensitive to look at very faint things. And in another mode, you could say, okay, well, now we're going to use it for resolution primarily. And in another mode, you can say we're just going to use it to do a quick survey and scan as much as possible over a wide area instead of looking at a very small area in much detail. So, yeah.
Okay, so in other words, in order to utilize its resolution to the maximum, the single dishes on the outskirts have got to be able to detect the signal and have got to be sensitive enough.
That's what I would expect, yes. But one needs to check that with a radio astronomer for me to say that with 100% certainty.
Okay, right, thanks.
Great, thank you, Richard. Does anyone else have any more questions for Francois? Great, then I'm going to say, Francois, well done. You did a fantastic presentation for us, and I was excited when we had the test earlier today because what I saw I really liked. But now I must just applaud you and say thank you very much for taking your precious time out to come and share this with the Cape Centre and the friends of Cape Centre. And we wish you all the best, and we would really like to have you back in the future, if possible.
Thank you. It was a pleasure. Thank you for inviting me. Also, especially to Kestrel, who told me about this the first time. And yeah, enjoy your evening, and good luck during lockdown. I hope there will be a time to meet all of you in person.
Yeah, definitely. We definitely hope so too, Francois. I guess, the next couple of months is going to be critical, and I think all of our Cape Centre members are really very eager to get back under the night sky and have some of our public stargazing evenings. But for now, we are really grateful for people like you that take out the time and effort to come and share their passion with us. Thank you very much. So,
thank you.
Guys, this brings us to the end of the formal presentation for the evening. So what we're going to do is we're going to just allow